So now that we've talked about integrating basic polynomials and defining what integration really is, we need to start talking about how integration is used. And the first way it's used is through the fundamental theorem of calculus. And the fundamental theorem of calculus has two different parts. So the first thing we're going to focus on is the fundamental theorem of calculus, part 1. All right, and this states that if our function is continuous on a closed interval of AB and it's differentiable within this same interval, then we can find the definite integral of a function. And you know you're being asked to find the definite integral of a function when that integral symbol includes an upper limit and a lower limit. And to find that integral value, you are going to plug in these upper and lower limits into the antiderivative and take their difference. So after last class, we need to talk about once again what the integral means. So as we discussed in class last, finding the integral is finding the area underneath the curve and the x-axis. And the definite integral is such. So let's look at this next example and consider the function negative 2x plus 3. Okay, it is graphed below. So we're being asked to find the area, okay, between the upper and lower limit of 1 and negative 2. So from here to here. Now, what we could do is divide it into two separate regions and find the area of this triangle and then find the area of this rectangle. So let's do that. All right, if we found the area of the triangle, we know it would be 1/2 base times height. So 1/2 of 6 times 3, and that equals 9. We could also find the area of the rectangle, which is base times height, which is 1 times 3, and we get 3. So based off of this, we're saying this definite integral equals 12 by adding those two together. Now, let's talk about it, doing it algebraically. All right, so the first thing we're going to do is find the definite integral, or the integral of the function. All right, so it'd be negative 2 over 2x squared plus 3 over 1x plus c, and we're finding it from 1 to negative 2. All right, so it's really negative 1 squared plus 3x plus c from 1 to negative 2. So negative 1 times 1 squared plus 3 times 1 plus c minus negative 1 times negative 2 squared plus 3 times negative 2 plus c. And we're using the fundamental theorem of calculus from above. So I get negative 1 plus 3 plus c minus negative 4 minus 6 plus c. So we have 2 plus c plus 10 minus c, and we get our answer to be 12. Exactly what we expected it to be. All right, I would like you to do the next one on your own. Find the area of the shape created from 2 to 5, okay, which is represented by the function of negative 2x plus 3. So from 2 to 5. Okay, so I want you to find it using both the area of the shape and the fundamental theorem of calculus. So if you did this one correctly, you would have gotten the answer of negative 12. Now, what's interesting is if you did it by breaking it up into shapes, okay, the area of the red triangle would be 1/2 base times height, which is 1/2 6 times 3, which is 9. And the area of the rectangle would be base times height, which is 1 times 3, and that equals 3. All right? Now, the key thing about this, though, is, all right, we have a value of 12 if you do it by finding the area between the shapes. But why is the answer negative 12 when we do the definite integral? And the reason that is because this area is below the x-axis. So our area here is below the x-axis. And so something of importance is that if the area represented by our definite integral is bounded above the x-axis, the definite integral will equal a positive value. All right? And if the area bounded by the definite integral is below the x-axis, the definite integral value would be negative. All right? Very important to remember that. Okay? So now let's look at the next example together. Let's find the definite integral from negative 1 to 4. Now, if we were doing it by looking at the shapes, okay, we have 2 triangles here. We have the red triangle and the blue triangle. So if we did the blue triangle, the area of the blue triangle is 1/2 base times height, which is 1/2 times 5 times 2.5. And the area of the red triangle is 1/2 base times height, which is 1/2 times 5 times 2.5. But we know it's negative because it's below the x-axis. Okay? So we'd get negative 6.25 and 6.25, which means that if you added them together, we would say that the value of this definite integral is 0. Let's see if that's the case, okay, when we actually use the fundamental theorem of calculus. So it'd be negative 2 over 2x squared plus 3 over 1x plus c from 4 to negative 1. So that's negative x squared plus 3x plus c from 4 to negative 1. So then that would equal negative 4 squared plus 3 times 4 plus c minus negative 1 squared plus 3 times -1 plus c. All right, so we'd get -16 plus 12 plus c minus -1 minus 3 plus c. So we'd get -4 plus c plus 4 minus c, which equals 0. The same exact answer. So this represents exactly what you've been asked to find. Okay, area underneath the x-axis needs to always be represented as a negative number. Area above the x-axis needs to always be represented as a positive number. And the definite integral, when found using the fundamental theorem of calculus, already takes that into account for you. Okay, you only have to introduce this negative sign if you're finding it geometrically. All right, so what I would like you to do is find the answers for the next two definite integrals. So based on the results of these 5 previous examples, what can we infer about the value of the definite integral and the amount of area bounded by the graph of the integrand and the x-axis? Well, there's 4 things we can infer. The first thing is, and as we defined in last class, the value of the definite integral, okay, is equal to the area of the region bounded by the function and the x-axis. Okay? The second inference we can make, which we already talked about, is if the value of our definite integral is greater than 0, all right, we know the region bounded by the function and the x-axis is above the x-axis and or it's larger than the region below. Okay? The third inference we can make is that if the value of the definite integral is less than 0, okay, the region bounded by f of x and the x-axis is below the x-axis, or it's larger than the region above the x-axis. Okay? And the final inference we can make is if the value of the definite integral is equal to 0, the region above is congruent to the region below. All right? So now what we'd like you to do, all right, is find the value of all of the definite integrals listed below. All right? And I just want to remind you that if you're ever taking the definite integral of x to the negative 1, that equals the natural log of x. This is one of those special rules of integration. Go ahead and do the next 4 problems on your own. So we can use the fundamental theorem of calculus to help us analyze using data tables. So pictured below is a table of values that shows the values of a function f of x and its first and second derivative for selected values of x. Use the information in the table to answer the questions that follow. So what is the value of the definite integral from 1 to negative 3 of the first derivative f of x? Well, remember, when you're taking the definite integral of the first derivative, you're finding the original function. So it's officially the original function from 1 to negative 3. So you're going to do f of 1 minus f of negative 3. F of 1 is negative 2. F of 3 is 1. I'm sorry, f of negative 3 is 4. So we get negative 6 as our answer. All right? Let's look at number 2. What is the value of the definite integral from 3 to negative 1 of f prime x plus f double prime x dx? So officially, just like you did with derivatives, you can separate this into two definite integrals, okay? And remember, the integral of the first derivative equals the original function. The integral of the second derivative is the first derivative of that function. All right? And you would find both of those values. So this would be f of 3 minus f of negative 1 plus f prime 3 minus f prime negative 1. And if you did that, you would get the answer of positive 3. Okay? I'd like you now to do problems 3 and 4 on your own. All right. Let's put this all together with some review stuff. And let's look at problems 5 and 6. Number 5. What is the equation of the tangent line to the graph of f of x at x equals 3? So remember, with the equation of the tangent line, we need the slope and we need the point of tangency. Well, we're going to know the point of tangency when x equals 3. All right, the original function has a y value of 1, so that's our point of tangency. We also should remember that the slope of the tangent line is equal to the first derivative at that x value. So the first derivative at 3 equals 3. Now that we know both our slope and our point of tangency, we can write our equation and leave it as such. Now I'd like you to use this equation of tangency to approximate the value of f of 3.1 for number 6, and then explain whether this is an over or under approximation. Once you are done with that, you are done with this video, and you can work on the corresponding worksheet. Have a great day, everybody.